from the KTH, and he's speaking about good modular spaces of AR stable curves.
Thank you, Jared. Thank you so much, the organizer, for giving me the opportunity to talk about this project in this wonderful workshop. And before I start, first of all, this is a joint work with Davide Gori, a student of Filippo Ignani, and Ludvig, Modin, which is here, student of Untitled. And full disclaimer, I will not going to talk about vector bundles at all. You need to bear with me for 40 minutes, only curves today, at least for 40 minutes, but I'm sure the next speaker will be very happy to talk about vector bundles. So I want to first somehow put our project inside the literature somehow, or explain why we started thinking about this state of the art. Yes, not on the board. And the questions that somehow, this is a very old question that everything started from here, is that trying to compactify the moduli space of smooth curves. And well, the first and arguably one of the most beautiful answer to this was given by Lin-Mumford with the Lin-Mumford compactification of stable curves, which is the moduli space, the coarse moduli space of a Lin-Mumford separated stack. But then, I mean, mathematicians don't usually stop at the first example, even if it's very beautiful. So there is all this business coming from this linear log MMP, which for curves is essentially what is called the acid kill program. That in the search for describing the canonical model for the stable curves actually provided a lot of some new compactifications of the moduli space of smooth curves. And it also does it in a modular way. So it produces actually some moduli stacks, and these moduli stacks have good moduli space, if they are arting or coarse moduli space in some cases, that would be compactification of this MGM, alternative compactification. But the point here is that you really need, so somehow as a warning, you really need good moduli space theory to do that. So this minimal program, at some point you want to do some more steps, and some natural linear reductive stabilizers appear, or positive-dimensional stabilizers. So you really need this theory of good moduli spaces to deal with the existence of good moduli space. So at first, I didn't want to write the following theorem because both the three authors are here in the audience, but sometimes we take risk, I guess. So this is a theorem due to Alper, Neisner, and Einloth, which I will write a very strict and somehow, not the full generality, of course, but this is the theorem that says essentially when you possess a good moduli space, it's actually a different only if condition. So if you have a finite type, affine diagonal scheme, stack over a field, then X has a good moduli space if and only if three conditions verify. So one is that X is locally linearly reductive, which, let's say in this generality, essentially means that your stabilizers at close points are linearly reductive. X is theta complete, and X is S complete. This somehow gives us a generalization of the theorem Kidmore for artist stacks, coming from the Lin-Mumford to artist stacks. And so a fact, which is important.
Sorry, separate.
Yep. Yeah, separate here. That's a good point. Thanks. Very important. This here, when here the author proved the existence of this kind of moduli space for some particular moduli space of curves, they do not use this theorem. This theorem was not out yet. It took 4 years after the last paper in the minimum model program, the acid kill program, to really to make this theorem appear. So somehow the proof there is very beautiful. I actually wanted to talk about it, but in the end, 40 minutes is not enough. So sadly I cannot really go through the proof of that because I want to give you an idea of how the proof of that works and to show you how our proof in fact is very different because it relies on trying to prove this criteria. So our idea is essentially saying, okay, this, sorry, here I should say. So our question is essentially starting from this theorem, which for all of you that knows about what this theorem, you know that this theorem essentially comes out from vector bundles. Like that somehow vector bundles are really the natural setting where this theorem applies, and you usually really do it for vector bundles. So our question was why we cannot do it for curves. So what are the obstructions, or we wanted to understand these conditions for curves. Of course, if you think about stable curves, these conditions are very easy, but we wanted to try to do it for what they're called AR stable curves, which is one of the possible generalization of mild singularities, like from nodes, you go to cast and tack nodes, which are also the singularities that are obtained in the first steps of this program. So I will very, very briefly, because of time, of course, try to give you an hint of what these two conditions are. I really hope that the authors of the paper will not be mad with me because I will not give really the right definition, but I will use somehow a more topological approach. So what theta complete means, maybe I should set some notation. Theta would be, say theta k would be the quotient of A1 of Gm with weight 1. I would fix a DVR. Say Q would be the fraction field, and K would be the residue field. Phi would be the uniformizer or whatever. So what theta complete means, you start with, you start with a diagram inside the stack like this. So you start with the generation of the DVR, which essentially means a map from a speck of R to your stack, and sum the generation for theta q, which means essentially just a map from theta q to your stack, with the condition that the generic fiber of theta q and the generic fiber of R, they have to coincide. So there should be a nice homomorphism between these two. So essentially X is theta complete if we can fill out the diagram. We can fill out the diagram. What this means, let's try to write some different colors. What we want is that up to extending your DVR, let's take an extension DVR, you want to find the generation over R here. So with the same DVR up to extending, so here, maybe if I want to put some names here, I have these points, which are points, you need to think of this as points inside your stack. This is somehow a topological view of what is happening. It's not enough to say this theta complete, but for the sake of this talk, I want you to understand the topological view. And you also want to find a theta map from K, where K would be the residue fields. Of course, because this is R, this will leave over a speck of Q, this will leave over a speck of K. And being X complete essentially means that for every such white diagram, you can fill out with a red diagram, roughly, again. Let's go with S complete. So you see, somehow this tells you how these two different types of degeneration behaves between them. Like you have standard degeneration over DVRs and this theta degeneration, the new ones that you can have. And this actually they can all appear for positive dimensional stabilizer. Somehow it's a very weird situation where you have 2 points that have the same residue field, the same field that defines them, but they are actually linked by the degeneration, which is something that it really happens when you have positive dimensional stabilizer. And this tells you how these two relates, how they communicate. S complete is more like your standard separatedness condition. So you start with two degeneration over the same DVR, and they coincide at the level of the generic point. And of course, if the stack was separated, these two would be the same, just by definition. But what you ask here, so X is S complete, if, again, we can fill out the diagram in the following way. So we can find the two theta the generation to the same point. Again, this is not exactly what S-complete means. S-complete is way stronger than what I'm writing. But for a topological view and for what we will need for this talk, this is enough. Okay, this
is there some uniqueness condition in how to fill them out?
If you think about the STR, so if you think about this as STR minus 0 and you want to fill out STR, the unique set comes out in this case, at least for the affine diagonal case. So uniqueness in that case is automatic. But you're thinking more like finding this point, or?
Yeah, I'm just saying you fill out the diagram. Is the condition that you fill it out?
If I'm writing topological, no, you can, if you want, you can go even further. But this is a, you will have different maps essentially. But at the level of, if you think about it in a real way, so as you should be like as STR, this stack that is the local picture of the plane mod GM, and you remove the 0, you want to fill out with a 0, there is a unique way. There is a really unique way because of sections and if they affine, if the diagonal is affine. So these are two conditions that I want you to keep in mind, and this again is somehow the more topological view of it, which is not enough to prove them, but it's still part of the definition. So now we are briefly will introduce what are the AR stable curves. That the reason why we chose those is that somehow I studied it for some enumerative geometry in showering. It's completely different approach, but we were wondering at some point, they have some GM, so we started wondering if they had a good moduli space. And this is essentially what we are going to do. So I will fix myself in characteristic 0, because the deformation theory can be a bit shaky for this kind of singularities, but to be safe, let's do it characteristic 0. So if you fix an algebraic closed field, C over K, a curve over K is AR pre-stable if it only admits AK singularity for K is less or equal than R. For those who don't know what AK singularity means, are essentially points that et al. Locally in the curve look like this. So you have to think about if K equals 0, this is just a smooth point. If K equals 1, this is just a usual node. K equals 2 is a cusp, K equals 3 is a tach node, and then you go on. And you have essentially two possible pictures. One is the somehow hyper cusp, and the other is the hyper tach node. Geometrically, they look really the same. They're just, the way you glue things is higher and higher, it's more and more complicated, even by the power of x. And you say that a pointed curve, and the pointing will always be, the marking will always be smooth and distinct, is AR stable if C is AR pre-stable, so it only admits this kind of singularities, and the twist, the log canonical bundle, so the twist of the canonical bundle, this is a LCI curve, it's particularly Gori sign, so this is a line bundle, you can twist it with the smooth points, this has to be ample. This is the only condition that we need. And the reason why we put this condition is just because there is a very easy thing to prove, is that with this condition you can run the usual Hilbert scheme argument to prove that now we say define MGNR to be the moduli stack of such curves. And the very easy fact to prove with this definition is that MGNR is a smooth quotient stack. So it's the usual thing that you do for stable curves. You just use the Hilbert scheme approach to prove this fact.
Sorry, but does this imply finite homomorphism of the curve?
No, not at all. We are going to discuss this very quickly, but no, they are definitely not finite. Right, so, okay, we have our stack, and the first question was, well, does this have a good moduli space? First things you want to check, what are the stabilizers? If you want a good moduli space, at least you want to have that the stabilizers are linear reductive. And we are in luck with this. The main lemma is that the connected component of these n-marked, an n-point in the area stable curve is, I would say, almost always a torus. So there's only one case where this doesn't happen, which is torus, which is for n equals 0 and r equal 2g plus 1, but we don't care about this. We will, I mean, you can just remove that from the stack and nothing will really change. But it's essentially always a torus. There's only one case where it is a gm times ga, and if one wants to be really brave, one could try to see if there is a non-reductive good model space, but not in this talk, I guess.
Sorry, Michele. So is this for any curve or for the ones that correspond to closed points?
No, this is for any curve, actually. Over algebraic closed field, and yeah, torus, like split torus, yes. Right. Oh, I haven't used that one. Okay, so before going to the two condition and see why the two condition fail in this case, and if they fail, and in fact they do, we need to think about the building blocks of this torus somehow. So what are the curves that have this positive dimensional automorphism? And so there are two main examples that I want to show you today. So one is take a rational curve, zero rational curve with a marked point, and which has one of these A2H singularities. Curves like these are actually classified by the following quotient stack. So it is an affine space is a representation actually mod GM. The idea is that when you normalize along these singularities, you have a GM, this is a P1 with 2 mark points, and all the possible curves that are of this form, they are classified by the crimping data that you are using when you squish this point. And this crimping data is essentially classified by an affine space, and the GM acts on this affine space. The cool feature is that every weight here has the same sign. I don't know, let's say 2, 3, 4, but the sign is always the same. They do not change the sign in this affine space. So this implies that there is only, and there are also, every one of them is strictly positive. There are no zeros as characters of GM. So this implies that there is actually a BGM here, and there is also the only point that has a positive dimensional automorphism, and it is the zero of the representation. This is a specific curve, or if you want a specific crimping data, which we call hyperelliptic, because it's also the only one that makes the curve being hyperelliptic, so having a 2-to-1 morphism over P1. Hyperelliptic crimping data. So this is the first example, and this is for the even case, but you can do the same for the odd case. So you can take two P1s, and you attach them by one of these A2H plus 1 singularities with 2 mark points. And what happens is that, again, the space classifying these kind of curves is just a representation mod GM. Now, you could expect to have two GMs given by the normalization, but the two GM need to coincide in the way where you're touching. So somehow one GM goes away from this. And again, you say the same. There is only one point, which is the zero of the affine space, where the stabilizer are positive dimensional. So here, again, we will call this the hyperelliptic crimping data. The only one that makes this one being hyperelliptic. Okay, now that we have the building blocks, let's try to find counterexamples to Theta reductive, or Theta complete to be precise.
Can one say more precisely what are the hyperelliptic ones?
What are, sorry?
Can one say more precise, give equations or something?
I mean, yes, so this affine space, for example, in this case, okay, this case is easier. What is exactly the crimping space in this case? It's just an identification between the two G, or in this case, H jet bundles at the 2 points when you normalize. The identity is exactly the crimping space corresponding to 0. You can identify in different ways, of course. You can take isomorphism which are not the identity, because these are Artinian rings, so you can have, I don't know, the various type of identification. You can classify them. and they are classified by an A, but the identity, so the one that corresponds in fact to the 0 of this affine space, is exactly the one. And you can just switch at that point. But any other ones, you cannot switch anymore, so you don't have the 2-to-1 cover of P1. That is the main issue. With there, it's a kind of this. It's somehow this the standard because to define this crimping, what you need to do instead is trying to find a subalgebra which is finite, such that this is finite flat of degree 2, and somehow the 0 correspond to the subalgebras given by this one. It's
Can you
like
read what you just wrote?
right, KT mod T to A, TH,
Oh.
and the map is just an in T to T square. All the other maps that you can, all the other subalgebra that you can construct will be T squared plus something else. And this will always be subalgebras of degree 2, but the one that has zeros everywhere is exactly the one that gives you the hyperelliptic. If you start doing this, if you start to prove which are the ones that give hyperelliptic, this is just the one. Which is also the one that gets the GM. That is the nice thing that happens. All right, so let's go with theta complete. So we started wondering, well, is it possible that these guys are theta complete? The answer is essentially no. So let's take a smooth curve, generic, whatever smooth curve you like, and you can attach to it one of those singularities like this. So it is attached by a node. That one was marked by in a point, right? In the mark point, you attached it, and here you have this A to H singularity, which is the hyperelliptic one, so the one that really has the GM. So what you can do, and I will show you in a moment why, you can deform this using a theta map to the curve here, where you deform the node, and so instead of having here some tail, you just get the singularity that is preserved, where when you deform the node, essentially the genus 0 curve, the rational curve here, the geometric genus 0 curve, will disappear, and the singularity will go into the smooth curve. I will show you why this is doable, but the point is that if you have something like this, you can always degenerate. If 2h is strictly less than the r you're fixing from the start, this can always degenerate to something which is worse. For example, 2h plus 1. And now there is a very, this is, if you think about this, is really the diagram, the white diagram that I wrote up there. And I want to fill it with some red things, but if you think about the geometry of the situation, by some lemmas that you can find in literature, these two singularities have to be preserved, and these singularities can only worsen. So you work a bit and you prove that there is no filling here. And this is really just a geometric thing. I'm not really working with maps from, this is really just a topological view, exactly as I described there. So there is no filling here that can be done. And the same example can be done using this kind of, the other situation. So you can take this, you can deform the two nodes together to get one singularity like this. But then if this 2h plus 1 is strictly less than the upper singularities you allow in your stack, this could go worse. This could be a 2h plus 2. So very briefly, why we can do something like this? Well, the idea is that you study the deformation theory of this curve. The deformation theory of this curve, the deformation space of the curve here, will just be the deformation theory of C0, the rest of the curve, with the marking here. Then there will be a deformation space of the node, and then you will have, well, this is a genus 0 curves, and the rest is the deformation theory of the singularities and the crimping data of the singularity. These are all the possible direction of the deformation theory. There is an action of GM here, which is given by this GM, the one that acts on the curve. And of course here, the weight is 0. There is no action on this side. Here, the weight would be, say, positive. Let's fix an identification with GM such that the tangent space of this point, the action of GM would be positive. But this will imply that this is actually negative, and if you do the computation, these two are always opposite signs. These are vector spaces, they have different characters, so it's not just one integer. But what I'm saying is that the integer here have always the opposite sides of the integers here. So essentially what I'm taking here, the picture that I'm essentially doing here, so here you have this, here would be your Tm plus Cs, here you have your Ts, and this is exactly the situation where your flows goes in one direction in one component and in the opposite direction on the other. So I can choose, for example, in this case, I smoothen the node, I can change the crimping data, but I need to fix the singularity. So what I'm doing is that essentially I'm going in this direction. So where I'm fixing the singularity will still preserve, but I will change the node and the crimping space. And the same you can do here. There's nothing really profound about this.
Can you move the board up?
Wait. I feel like using a lot of...
No, the lower board up.
The lower board up. Yeah, that's true because
Because
yeah. Okay, 15 minutes maybe. Right. So one could start thinking, okay, this implies that our stack do not have a good modular space, or at least it's not Theta complete. Where did I put? But well, I mean, there is a possible thing you can do. You can just say, well, I will remove something from the diagram, from the upper three triangles. Say, for example, I can remove this one from the stack and this one, in a way that the stack now, you cannot construct this diagram. It doesn't feel like a very nice idea to start from counterexample and start from removing things. But it's actually, I think that in Italy, like geometry, once upon a time was exactly working like this. You were trying to find counterexample to things, you remove all your hypotheses and then you arrive at the conclusion. But anyway, so the point is, why we don't remove these two? Well, these are kind of the generic situation. If you want to allow singularities up to R, you cannot really remove the generic situation when your singularity is here. So you don't really want to remove this situation. So you are forced to remove these two. And then you can start to wonder, well, what about if I remove these two? Is this have a possibility of a good modular space? The answer is still no. And the counterexample now is as complete though. Because when you remove things, you can't lose this completeness. This is the reason. Let's try. I know I'm drawing a lot of picture. Maybe you're not satisfied with this, but let's say that I have the situation that I had above. So I have these two H singularities with a GM. So this is one of these hyperelliptic singularities. And by this picture, essentially, by this deformation picture, I have two different ways of arriving at the singularities using a theta map. One is where I deform the node, changing maybe the crimping data. So here I will have something like this, which is one of the two things that I have. But the other is when I instead go in the other direction, I deform the singularities, but in that case I need to fix the crimping data and fix the node. So the other direction would be something like this, where I deform the singularities, I obtain a genus H curve attached by a node, and the wonderful thing is that because I'm not changing the crimping space, this will be actually an hyperelliptic curve. This would be a non-hyperelliptic curve, meaning that I would have a 2-to-1 cover of P1, and this would be a Weierstrass point. And now, I will not have time to convince you, but there is a common generation to these two, and the reason is that essentially, locally, what we are doing is exactly removing the zero, is exactly what you see in this picture. So we are either going from this way, or we're going essentially from this way, changing, of course, the sign. And what I'm claiming is that if I remove the zero, this is not as complete anymore. This is, if you think about the case of A2 with GM, where weights 1 and -1, if you remove the zero, this is actually, it has a quotient, but the quotient is non-separating. It's the two origin affine lines. So this is exactly what happened here. If I remove this, I need to remove one of these two, otherwise I'm lost. But again, this one I don't want to remove. This is a generic one, and I really don't want to remove. So I really need to remove something, and this something will be this guy here. So at the end, all the upshot is to say, we need to remove. These we call hyperelliptic tails of genus strictly less than R mod 2. The reason why we put this strictly less R mod 2 is because this contract sample that was here is only working where 2h is less than R. Because if you're already at a singularity that's over, is exactly, for example, equal to R, you cannot degenerate to a singularity which is worse. So the contraexample don't exist in that case. So this is the only thing we can say here. And here, also what we need to remove, the same situation will happen for bridges. So somehow you see that these even and odd cases reflect in these two singularities, in these two cases. So this we call hyperelliptic bridges of genus strictly less than R minus 1 mod 2. Again, for the same reason, here we had that this 2h plus 1 was strictly less than R. So I was cheating a bit.
Does the condition of hyperelliptic tail include the Weierstrass point?
Yes, it's very important.
Here do the points have to be conjugate?
Exactly, for the bridge also the points have to be conjugate. Yes, this is all following from this local
So
description.
it really has to smooth to something with a double smooth.
Yeah, exactly, with a double cover, and the point would be exactly a Weierstrass point or a 2-point exchange with involution. So something I want you to notice that if I do this example in a situation where you have this kind of bridge, but these two are two disconnected components, I can try to run the same counterexamples, and here I will have the two connected components now meeting these singularities, but now this one cannot worsen now, because you really have two reducible components attaching the only one point, and this point now cannot be really worsened up. So in this case, there is actually no counterexamples. You can really, I mean, this is not a proof, but I assure you that here, there is really no counterexample you can construct. So somehow what I should say here is not really hyperelliptic bridges that we need to remove, but there are the non-separating hyperelliptic bridges. So there are the hyperelliptic bridges that when you remove them, you still get a connected curve. This same, I mean, you can also remove the one that are separating. You will get something smaller. But the reason why we want to keep the separating one is essentially that what we end up getting would probably be an algebraic space instead of a scheme. But this is still very work in progress. For now, somehow we wanted to find the biggest or the easiest stack for which we can apply these criteria, but it was also not the one that you start in removing everything that you like. I want to say, it is very important that I say it now, is that these two conditions are actually, did I cancel it? No. Right. Yes, these two conditions are actually, so all the stacks that appear here, they are substacks of, open substacks of this MGNR. So the stacks that appear here, at least for the first steps, they need IR singularities, and they are all curves which have the canonical ample, and they have this IR singularity. So they will be open inside our stack. And in fact, they will be open inside these stacks, even if you remove those two, because these two conditions, which in this case they appear because there is a line bundle telling you cannot include them, we actually show that essentially this line bundle wasn't really saying that these two, they cannot appear, because these cannot appear for a geometric region. Of course, in these cases, in their paper, they use the line bundle to prove that it exists a good model space using variation of GIT, and so somehow the line bundle tells you that you can, as complete reductive needs to appear. But what we said is that somehow, at least for these two cases, you don't need a line bundle to tell you that this cannot appear. It's somehow already in the geometry of what you're considering. So I can finally go to the definition of our moduli stack. So the notation is still really a work in progress as well, but we call this MGNR strictly less to be the moduli stack of genus G and marked AR stable curves. So if you want AR stable curves, such that these two conditions holds. So you don't have we need to be more precise. Here you don't want hyperelliptic tails, but you also don't want things which are hyperelliptic and are attached by a bias thrust point, but they can be attached also non-nodally. So they could have some attachment like, maybe I need to be precise here, but what we remove for other counterexamples that we find, you need to remove also things that are like hyperelliptic. This is a bias thrust point, but attached by some higher order nodes, so TAC nodes. And for an example of this, somehow you can think about taking this case where we actually remove only the one attached by A1s. And if you think of a limit case of this, somehow you ended up here. If you have like an hyperelliptic curve with attached by two nodes, which are exchanged with involution, when you go to the limit, you also want to remove the case where it's attached by a TAC node. There are examples that show you that you actually can remove higher order attachments. I mean, here there are several. In particular, in the n equals 0 case, you can form very strange things. But so this is not the full list of counterexamples that we've found. There are like 5 or 6. But these are somehow the most natural, because they were also the ones that were really clearly removed in the asset kill program for reasons that were essentially a line bundle. But here what we show is that actually it's geometry of the curves that tells you that you need to remove them. So, okay, I will write down the theorem, and which is, well, this guy has actually a proper good modular space. And at the beginning I was planning of giving a proof of at least an idea of at least Theta reductivity, and I will try. I thought it would take more time, but I will try to give an idea. I will leave this one. No, but here you cannot see. And the very nice thing is that we can prove that this actually exists as a good modular space. I still need to finish the computation, to be fair, but what I believe that the Picard group of the modular space, in that case, would actually be trivial. So there are no line bundles, so it's definitely non-projective. And we still don't know if it is a scheme or not, in fact. We still don't know. But that would probably be part of the paper when, if we'll ever come out. It's not a long time that we're working on this. But so for Theta reductive, I have 3 minutes. Let's see, Theta complete, sorry. I still need to change my mindset to the right definition. But the idea is the following. So there is you start with a diagram like this. It's a very rough idea. I'm sorry for what essentially I'm about to say. But so you have your, let's see, C, this would be CQ prime. So this is a curve over Q, this is a curve over Q, and this is a theta Q degeneration from CQ to CQ prime, and this is R, and this is CK, the residue field. So the main idea to prove that this actually fills up is an induction procedure. So because there is a GM here acting, say that this is non-trivial degeneration, otherwise this is automatically filled up. Because this is a GM acting, which is a non-trivial GM, and we know completely what are, I haven't said it, but we know exactly what are the automorphism, and when this automorphism appears, well, we can prove that here there should be a section, say as Q prime, that goes in one of these singularities which are hyperelliptic. So, because of what we removed, essentially what we can say, using a deformation theory argument, is that this section actually lifts to this case here. So, the section that was in the special fiber theta Q actually needs to lift up to very small cases that we can treat very easily. But it really lifts up here, and again, because of the condition we put, it's actually not too hard to prove that this section actually close up. I mean, it's always close up, but the thing is that close up in a section, and all these 3 sections are of the same singularities. So what you end up having, essentially, if you want to look at it like this, it's a section which is an equisingular section. So it's a section that goes to the same type of singularity in any of the 3 points. And now what you do, well, you can first normalize, because it is equisingular, and then you stabilize, so you contract the P1s that are free, and so you reduce the case to a lower genus case, and this is where the induction procedure essentially, okay, I have 4 seconds, where this induction procedure tells you that here you can fill up. So this one somehow, you can fill up over theta r. And what you need to do is now reconstruct this, the C over there. But the fact that the crimping space and the fact that these singularities are completely defined by the crimping that you use, and the fact that the crimping space is affine, is really helpful because you can use that affine maps preserve theta reductivity. So you just have, sorry, theta completeness. So you have theta completeness down C, or over the lower stack, over C. You have an affine map, and then you just say, okay, because it is an affine map, the one above was also theta complete. Sorry, it was very, very fast, and maybe I should have went to this detail, but yeah, thanks.
Other questions?
So do you recover exactly the model spaces of class?
No, we recover something bigger. In fact, they have because they work with essentially GIT or with this line model, which is a very important part of it. You get something which is quasi-projective, well, projective because it's proper. And what we get is essentially something which is bigger, and it is contracting part of the things that they have in their modular spaces, and they are contracted so much that you can end up having an algebraic space instead. Because essentially, for example, they will remove all the elliptic regions without a non-separating condition. So for this is part, but they will also remove more. So you're definitely getting something different, which will be a smaller thing. Well, smaller in the sense that will be contracting from their modular spaces. It will be a contraction, yeah.
What do the deformation spaces of these AR singularities look like? So how bad do we expect these spaces to be?
The modular space, or no, you say the stack?
Yeah, I guess I'm asking for both.
I mean, the stack is really just a smooth stack, and the deformation are just, I mean, for every type of singularity, like that one, you really have always the crimping space, and then the usual, like, T1 of the singularity. So when, like, I don't know how, like, when you have a singularities, you always have this, I guess it's...
Sorry, you're saying that the moduli stacks are actually smooth?
Yeah, all the modular stacks are actually smooth. Yeah. Because these are all LCI curves, so you are completely unobstructed. Yes, yes. And yeah, you have, I mean, part of the tangent space would be like the local x1, which is like the deformation space of the singularities, which is completely understood. And then there is the crimping space. So how many crimping data you need to choose to glue the things together, or pinch in the case of hyper cusps. And then you have the deformation of the normalization, essentially, exactly as you have for nodes.
David?
Could you do some sort of wall crossing when you increase R?
So this is exactly, I mean, I explained how we prove that reductive. To prove S completeness, we need to use this as, you need to use this wall crossing. So there is this picture, and that's why I guess no one really, no? Yes. Really, no one asked, but we can do the same definition instead of putting less, or putting less or equal. And this less or equals would give less or equal there. And the idea is that now you're really getting some wall crossing scenarios. So you have this, for example, R minus 1. This embeds inside the case with R. And here you're really starting getting a wall crossing with the varying the R. Now this is somehow a discrete wall crossing because the R now are just integers. But the way we actually prove that as a proper good modular space, so for example, the puncture inertia, the separatedness of the good modular space, essentially using the one before and seeing that the good modular space here at this map and proving that this map are actually proper so that you can really, right, here should be swap R, and G, and S. But yeah, so somehow this is it's strange to say this, but this is somehow a coarser wall crossing that happens here. Somehow we are doing the steps, only increasing the singularities. Here, somehow it's supposed, when you go to, it's conjecture that when you go to higher, when you go closer to the canonical model, you expect this to have more walls inside the same, inside the stack, which the same singularities, say. So somehow ours is a more coarser wall crossing, and in fact you get something which are not we expect that they are not even schemes. They're definitely not projective, but we expect they're not even schemes.
But in as a key, I mean, then you also get beyond AR singularities, right?
What?
In the ASCII program, you have
Yeah, it's conjecture. At some point, you even leave the the ER singularities. Yeah.
I have a question myself. So you kind of gave us some evidence that the stack of AR stable curves is not Theta complete because of these pathologies here. You have to remove one or the other. What if you were to consider sort of enlargements of this, like adding additional singularities other than AR singularities, so that maybe there is sort of a common degeneration of those two?
So in this case in particular, for example, I spent all the time learning about AR singularities, so I'm not sure what about the other ones, but I mean, this is a genus zero curve, geometric genus zero curve, so it will feel weird if exists a degeneration to some other singularities. Well, then it could happen, I guess. You can have, one, I guess you really need to understand, like, take another singularity, say that, I don't know, D singularities. There exists a degeneration where you don't change the genus of the singularity, like the local genus singularities, but you pass from D to A. This, I guess, is possible. I think that there is the work of Asset and Casalina Martin, where but I don't remember if you can really do it like keeping the genus. This I don't remember, I should check. But it could happen at this point, yeah. Even though here you have like two different singularities, right? With different genus, that's the main. Yeah, I cannot answer precisely. Yes.
Another question.
So the original stack NGNR, does the boundary look so singular curves? Is this a divisor or?
It's still a divisor. Yeah, I mean it has all the singular curve, and you can define exactly the same way you would do a stable curve. So you take the universal curve, you take now the differential, you do the fitting ideals of the differential. In fact, it's really cool that you can define every step. So you take like singularities or singularities from cusp on or tach nodes on, using the fitting ideals of this, this subsequent fitting ideal of the things you get. But it's still a divisor. In fact, the reason why we know that the Picard of this guy is 0 is essentially because the Picard group of this one would be the same of MG and R is the same as the Picard group of MG and bar, because everything lives in codimension 2 and they are smooth. So we really can check that there is no Picard by taking all the line bundles and checking that every time you can find a curve where there's some GMs that do not fix the line bundle, like there's a non-trivial action on the line bundle from the GM, so that there is nothing descending down to the good modular space.
Let's take a peek at